Let's look now at the data structures that are described in the two reference papers of this lesson. The two papers describe the kernel and user-level implementations of threads in the SunOS 5.0 kernel of Solaris 2.0. So Solaris is the operating system. Sun, where this work was done, no longer exists. It was bought by Oracle in 2010, but it was very well known for the quality and stability of its Unix distributions. It was also one of the leaders in introducing new and revolutionary features into the kernel. And this is why we're looking at its threading model. This is a diagram from Figure 1 in the Stein and Shaw paper implementing lightweight threads. And it illustrates quickly the threading model supported in the operating system. Going from the bottom up, the OS is intended for multiprocessor systems with multiple CPUs, and the kernel itself is multi-threaded. There are multiple kernel-level threads. At user level, the processes can be single or multi-threaded. Both many-to-many as well as one-to-one mappings are supported. Each kernel-level thread that's executing a user-level thread has a lightweight process data structure associated with it. From the user-level library's perspective, these lightweight processes represent the virtual CPUs onto which it's going to be scheduling the user-level threads. At the kernel level, there will be a kernel-level scheduler that will be managing the kernel-level threads and scheduling them onto the physical CPUs. We will now look a little more closely at the user-level thread data structures. They are described in the Implementing Lightweight Threads paper by Stein and Shaw. This does not describe pthreads, the POSIX threads, but it's a similar type of user-level threading library. When a thread is created, the library returns a thread ID. And this is not a direct pointer to the actual thread data structure like we implied before. Instead, it's an index in a table of pointers. It is the table pointers that in turn point to the actual thread data structure. The nice thing about this is that if there is a problem with the thread, if the thread ID were a pointer, then that pointer would just point to some corrupt memory, and we can't really figure out what's going on. Whereas here, by having the thread ID indexed into a table entry, we can encode some information into the table entry that can provide some meaningful feedback or an error message. The thread data structure, we said, contains a number of fields: registers, signal mask, priority. There's also the stack pointer, of course, that points to the stack. And then there is the thread local storage area. This includes the variables that are defined in the thread functions that are known at compile time, so the compiler can allocate private storage on a per-thread basis for each of them. The stack itself, its size, it may be defined based on some library defaults, or the user can provide a stack. But basically, the size of a lot of this information is known upfront at compile time, so we can create these thread data structures and sort of layer them in a contiguous way. And that can help us achieve locality. It can make it easy for the scheduler to find the next thread. Just has to basically multiply the thread index with the size of the data structure. The problem, however, is that the threading library doesn't really control the stack growth. So it doesn't inject itself between any kind of update on what gets written on the stack. And then the operating system itself, it doesn't know that there are multiple user-level threads. So it's possible that as the stack is growing, that one thread will end up overriding the data structure of another thread. If this happens, the tricky part is that the error, the problem, will be detected when that other thread gets to run. However, the cause of the problem is a completely different thread. So this makes debugging a little bit tricky. The solution that was introduced in this paper was to separate the information about different threads with a so-called red zone. This really refers to a portion of the virtual address space that's not allocated. So if a thread is running and its stack is increasing, if it tries to write to an address that basically falls in this red zone region, then the operating system will cause a fault. Now it's, however, much easier to reason about what happened because the problem was directly caused by the thread that was executing. So it's easier to do root cause analysis and to fix the problem.